Okay, so I think we'll start. So good morning all. So welcome to the fourth day, and I hope that you guys are keeping the pace not lost completely. Okay. So today we have three speakers in the first session. So today we mostly will look at some technical part and some science part which is related to SKA. So the first talk will be the nearest star. It's related to nearest star to us, the sun, and the activities what sun goes through, and the SKA what it will do with it. So in the second talk we have Professor Surajit Pal from Mahe. So who will be talking about more on continuum, and of course we have Jagdeep who will be continuing from tomorrow's technical discussion more on receiver side. Okay, so I welcome Professor Bhargav Vaidya who is from IIT Indore itself. Okay, so please Bhargav.
Thank you. Am I audible? Yes. Great. Thank you, Naren, for this kind invitation. Do you really need to talk on mic, or I can be actually loud? Because this will be too loud in one go.
We need it for the recording.
Oh, I see. Then let me put it here. Okay. Is this better now? Otherwise, there's an echo. Okay. So, first of all, good morning and welcome to the fourth day of this workshop. So, as Naren mentioned, the first two lectures will be focusing on science. I think most of you are PhD students. So today I will take you to the journey between sun and earth, and then we will look into certain aspects what exists between sun and earth, and try to also see if we can study these aspects using radio band, and what way we can study these aspects using radio band. Okay. So I don't think it'll work. So this is for the laser. Anyways. So what I have planned for this particular talk, I will start with what is our sun, and mainly focus on the impact of our sun in terms of space weather. Then I will look into different kinds of observatories which are existing in the current day and age, which looks into the sun itself and the environment around the sun, both from the space-based perspective as well as from ground perspective. Then we will look why, even in spite of having these many observatories both in space and ground, why it is important to basically study the heliosphere, which is the region between the sun and earth in today's lecture, that is the inner heliosphere. Why do you want to study it in the radio wavelength? Why do you want to study this? What is the importance of using radio wavelength to study this? And then I will talk about some basic physics of where this radio emission will come from. Okay, so some basic physics aspects of the origin of the source of this radio emission. And then I will talk about the two classical methods which are used as far as radio observations are concerned, and what kind of clues do they give in terms of understanding the heliosphere in general. Okay, so let's begin. So if I may ask, how many of the PhD students are working on stuff related to sun, heliosphere? Can you raise your hands?
There is no PhD students.
They are master students.
Mostly, masters and BTech second year students.
BTech and okay, fine. So how many of your master students are working or have been working with sun or heliosphere? Anyone? No projects on sun? Okay, one. Only one. That's it. So this will all be new for all of you. Great. Perfect. So let's look at our sun. So our sun is the nearest star, about 1 astronomical unit away from Earth. The sun basically emits emission in almost all wavebands, mostly in the optical. That's what you see, and you can actually get the what you can say the emission or the temperature of the sun from its spectra by assuming it's a black body. You can use your Wien's displacement law, and you can actually get the temperature of the particular sun. But if you look at the sun in totality, from the inner part to the outer part, it consists of several layers. So we know that our sun is a typical star which has an inner core which is very, very high in temperature. About 25% of the volume is consisted by this inner core. This is where all the fusion reaction happens, and you generate photons of very high energy, and the temperatures can go up to very, very high over there, and you can generate a photon of very high energy which will actually traverse through this radiation or radiative zone before it reaches what is basically known as the convective zone. This is where the convection happens. So there are different modes of heat transfer from the core of the sun to the surface of the sun, and that's what the photon we observe. But the beauty is that the photon that is generated at the core of the sun takes about several years to actually come to the edge of the radiative zone, because there are a lot of material through which the photon has to kind of diffuse and come out at the surface of the radiative zone, at the edge of the radiative zone, and then there is a very thin layer which we call the tachocline. The tachocline has a maximum shear. You understand what is shear? There is a large difference between the velocity in the radiative zone and the convective zone. So you generate a huge shear, and at this tachocline you also generate magnetic fields. So our sun is a highly magnetized star, and the generation of the magnetic field happens at this tachocline. And then when the magnetic fields are generated, these magnetic fields are kind of like a boiling motion comes up from the inside of the convective zone on the upper layer, on the photosphere. So they kind of rise from the tachocline through the convective zone on the photosphere, and kind of like bubbles you have seen on the surface of the water. These bubbles, like magnetic bubbles, pops up from these things. Now these bubbles can be large, which we call as the active region, or they can be small, which we call basically just nanoflares or small quarks and regions. Now, if you look at the surface of the photosphere, there are also interesting regions which are essentially, you may have seen, they are called sunspots. So what are these sunspots? They are very, very dark region on the surface of the sun. But the fact that these are dark, we have to look at, but they are having extremely strong concentration of magnetic fields. And usually sunspots exist in pairs. So you have a one sunspot here, one sunspot here. So you can think of a magnetic field kind of getting attached here like a bubble, which is popping out from the surface of the sun. Okay? So that's what sunspots are. Sunspots are strong concentration of magnetic fields, and because they have strong concentration of magnetic fields, they are darker because most of the energy is basically governed by the magnetic fields and not the thermal radiation. So that comes on the photosphere. So this is something what we see. The photosphere is what we see as far as the optical light is concerned. And then you go beyond the photosphere, you have all sorts of other atmospheric regions which are essentially known as the chromosphere and the corona. Now this is, and then finally the corona just basically extends into what we know as the solar wind, which actually comes to Earth, and we are detecting it at the surface of the Earth. Right? So this is a general understanding of our sun. Of course, with the time permit, I can, even if you have questions, I can go in details of it also, but we can take up it later. So let's look at the sun in other wavelengths, because this is what sun has been looked up into in other wavelengths, because it also gives you an indication of what the sun is all about. And most importantly, there is a very, very nice observatory called the Solar Dynamics Observatory, called the SDO. And inside this SDO, you have an atmospheric assembly interface, so AIA assembly, which kind of looks at the sun in several wavelengths. Okay, it starts to look at the sun at different optical and UV wavelengths. So you can look at the sun at 4,500 Armstrong, which is basically sensitive to 6,000 Kelvin temperature which exists on the photosphere. So you can see the photosphere. You can see very beautifully these sunspots here, very nice. And there is some limb brightening, which is also a very interesting feature. Then if you go to slightly higher wavelengths or lower wavelengths, that is higher temperature, you can now look up into the regions of the upper atmosphere. You can now start to see some turbulent features. And if you go to much higher and higher kind of temperatures, you can actually see regions of intense activity that are happening on the surface of the sun. And you can see these beautiful features, especially on the edges. These are plasma being channeled on the magnetic fields. Okay, so this is basically you are seeing now in the upper transition, and then if you go to much smaller wavelengths and extremely high temperature, you still see emission, which is fascinating because this kind of region is much away from the photosphere itself. So if you look at the typical log of temperature, which is plotted on the y-axis with the height from the surface of the sun. So this is basically 0 is the photosphere, and if you look at the temperature, it is typically of the order of 6,000, so it's about 3 point something. And then you look at it as you go much ahead, like about few thousands of kilometers, the temperature actually increases. Okay, it doesn't decrease. So it's not like the light is emitting out and is basically, one would expect that it is adiabatically expanding, so the size will increase and the temperature will decrease. No, it's not the case. So actually, the temperature keeps on increasing, and in fact it reaches by 3 orders of magnitude, or almost 2 orders of magnitude higher at about 5,000 kilometers away from the surface of the sun. Now this is a very classic problem in solar physics. It's called the problem of coronal heating. I think Rohit is coming next week, and he will also touch upon this aspect, and he will mostly focus on near sun. I am aware that he will talk about solar radio bursts and so on and so forth, which I have not focused on this particular talk. I will focus on something much ahead of the atmosphere. But this is what the atmosphere looks like. So this is how you can basically map, or at least see the different layers of the sun by just one assembly, which is the AIA, and it has given immense understanding of what really happens on the surface of the sun. But of course, sun as a star to study is very good, but nowadays it has become an extremely important aspect because of the contribution the sun gives on space weather. Okay, space weather is, what I can tell you, is an environment around Earth that is impacted by the activities that goes on the surface of the sun. Now this is something, why do you want to study space weather? Because space weather really has an impact on the space assets that are surrounding our Earth, like our own satellites, communication, airplane parts. I'm sure you guys have heard about SpaceX. Everyone has heard about SpaceX. In February 2022, they lost about 39 satellites, only because of some mild activity on the surface of the sun. What it did is, it created, you can think of it, basically it created an atmospheric drag, and it kind of pushed the satellite out of its dedicated orbit, and then they kind of swung and fell back onto the surface of Earth. So such activities or such events are extremely important, so that's why it is important to study the sun in totality, and particularly how the sun impacts the Earth, or what is there in between sun and Earth that impacts the Earth. Right, but what is the challenge? Of course, the challenge is it's very difficult to understand because of the complex physical processes that go into. As you can see already, the sun, we do not understand the coronal heating problem. Secondly, there are lack of observation and data, and this is something which you will come across, and that's where radio wavelength plays a very, very important role. You see, the sun-Earth system is a completely 3D system. It's like a sphere, right? If you take sun at the center and Earth around it, it is basically like a sphere. If you want to understand the system in totality, you want to understand the sphere as volumetric object. But the problem is, being on Earth, we can only sample certain regions or certain points in between this. So we cannot get a total picture of the sphere. We have to go out of our solar system and see what is basically happening. That's not possible. Okay? So basically, that's where the problem lies. And now, there are several, space weather has become so much of an active field of research that there are already several processing centers in countries like US, China, European Space Agencies, Japan, and so on and so forth. And India is also trying to go in this direction to some extent. But then, what are the drivers, or what drives space weather? If that's the question that we ask, because you see, ultimately, if you want to understand space weather, you want to understand what drives space weather. and how we can actually quantify or constrain space weather using observations or data or modeling or whatever way it's possible. So there are several aspects that drive space weathers. The first and the foremost are the solar flares. So these are like bright spots or bright happenings which we saw earlier as well. I can show you here. These are now, you can see a bright signature here. These are solar flares. So there's a bright emission which is coming where you have an active region or where you have a lot of sunspots, and this flare kind of region basically can give rise to very, very highly energetic electrons which can basically move and impact our Earth environment. The second and the most crucial are the coronal mass ejections. Now they are fairly common during the active region of the sun. So basically our sun does not behave in a steady manner throughout all the time. Okay, it has an activity cycle. Okay, it has basically an 11-year activity cycle. Our sun behaves quietly, nicely, and then after every 11 divided by 5.5 years, it becomes into an active phase, and then again decays, and then again it starts to become inactive and decays, and so on and so forth. So it's almost an 11-year cycle with which the sun is kind of behaving. And in its active phase, it emits significant amount of coronal mass ejections. So these are like material flow being thrown out of the sun that can traverse towards Earth and hit us and impact our Earth's magnetic environment. So this is also very important, and this is really the major space weather driver, and we have to understand this using either observations and mostly radio observation, and this I will come to when we discuss of the impact of radio in observing this inner heliosphere. So the third part is the solar wind, which is being continuously ejected from the surface of the sun. Okay, so you are always constantly bombarded with solar wind, and the solar wind can be fast. That means having velocities more than 400 kilometers per hour, 400 kilometers per second, and slow, which is speed less than 400 kilometers per second. So in general, solar wind fast winds can go up to 700, 800 kilometers per second as well. And when the solar fast and slow wind interact, you have something called as SIRs or CIRs, which are essentially the solar interacting regions and so on and so forth. You also have solar energetic particles, because these particles can be inserted into the inner heliosphere because of, let's say, flares or such coronal mass ejection which is driving and impacting the plasma that is intervening between the sun and Earth. And then finally, as I mentioned, it has a solar cycle which basically impacts on a much larger scale or a much longer time scale, and that's why we call it as an impact on the space climate. So these are the major, what you can say, space weather drivers that control how the environment around our Earth will behave due to the sun itself. So this is a very nice overview, I would like to say, of how these regions, the sun, heliosphere and the Earth, are connected with or interconnected with each other. As I said, the sun, these are the space weather drivers from the sun, and there are several observatories, as we will look into, which are closer to the sun. Okay, Messenger is, for example, on the Mercury, and so is Bepicolombo, and you have Vex in Venus, and so on and so. Parker Solar Probe, Solar Orbiter are being sent closer to the sun, and so on. So you have basically, these are, as we discussed, these are the different space weather drivers. Now these space weather drivers input energy into the heliosphere, which is the region between the sun and Earth. So this happens, these are all generated by the sun, and then the energy is inputted into the heliosphere. And inside this heliosphere, you have all sorts of activity happening. As the CME propagates, as the CME moves, it can generate more, what you can say, energetic particles. It can interact with the solar wind which is existing. It can basically kind of insert drag force, or it can impact the the Earth environment, and so on and so forth. So how do we understand what is happening within the heliosphere is a big no data zone up till now, or at least very limited data zone till now. And then you have basically the impact once all these drivers comes and hits the Earth. What sort of impact does it have? So the output of this heliospheric model is basically the energy input into the Earth system. Some magnetosphere ionosphere coupling. As you know that our Earth has magnetic fields, so it has a protective layer of which this is blocked, and then you have all sorts of effects on the ionosphere and magnetosphere and so on and so forth. So this is a very nice overview of what this space weather is all about and how these regions are very well interconnected. So we need to understand each and every aspect if we really want to kind of have any idea on what space weather is all about. So of course, people know about this. People have been trying to find ways to understand this in totality, but it's as I said, it's an extremely difficult problem because you have to go outside of our own solar system to look what is a total 3D space. So several missions have been launched. Some of them have been recently launched. For example, Punch, which has been just recently launched. Several of them are about to get launched. I think IMAP, I think is just launched or is about to get launched. And then you have all sorts of missions. So many of these missions like WIND, IMAP, ACE, they are in a point or in an orbit called the Lagrangian 1 orbit. Okay, so this is basically a stable point that lies between the Sun and Earth, and it is an extremely advantageous point to just continuously look at the Sun. Because if you want to study the Sun, you want to continuously look at the Sun. ऐसा नहीं है कि एक बार देखा and then you go around and then you don't see the Sun. You have to look at the Sun continuously. So that's why you place it in L1 orbit, and there are several of these satellites there. Couple of them, Solar Orbit and Parker Solar Probe, one is by NASA, one is by ESA, has been injected in the inner heliosphere. So essentially you have just two data points. In this whole sphere, you have only 2 points which you are actually seeing at any particular instant of time, because the data is only collected at those 2 points. Okay, so imagine how much sparse there is data which is not available, which connects between Sun and Earth. And there are also many missions like MMS, THEMIS. All these missions study the impact of the space weather in the Earth environment. Okay, so these are all missions which have been studying the impact as well on the Earth environment. So you know that there is a significant coverage, but not enough to understand space weather in totality. Of course, India also in 2023, I think, we launched this mission called Aditya L1, which was launched in September 2, 2023 using a PSLV satellite, Polar Satellite Launch Vehicle. And it reached the L1 Hello orbit in January 6th, 2024. So it's about more than a year now, it's in the Hello orbit observing the Sun. And it has mainly 7 payloads. 4 are what are known as remote sensing payloads. So that means you look at the Sun from far away. That's remote sensing. You're basically looking at the Sun from far away. And there are 3 payloads which are called in situ payload. That means you are measuring at the position of the satellite whatever material is coming from the Sun. So you are actually measuring it like a thermometer. If I put a thermometer here, you can measure the temperature, something like that. So that is in situ. So that is 3 are in situ, which are aspects which looks at the solar wind, PAPA which looks at very high energetic part of the solar wind, and MAG which measures the magnetic fields. And the 4 remote sensing mission payloads are VLC, which is nothing but a coronagraph. A coronagraph makes a fake eclipse and it kind of occults the Sun to see what is basically happening around the Sun. Then you have SOOP, which looks at the ultraviolet part, so in the chromosphere, and the SOLAX and Helios are X-ray kind of payloads which study soft and hard X-rays coming from the flare. So this is basically a mission to study, a first observatory class mission to study our own Sun, and it has kind of opened up this whole avenue of space weather as far as in India is also concerned. But in addition to that, traditionally, India has been doing a lot of solar physics research with ground-based observatories as well. And to list a few of them which are already existing, we have this Udaipur Solar Observatory, which is in PRL, which is in Udaipur. It's a beautiful place. It's an optical observatory. You can actually look at the sun, the surface of the sun, the sunspots, and do a lot of studies over there. And traditionally, the sun has been studied in radio bands with an Indian telescope missions, of course with UGMRT as well, but UT radio telescope has been fundamental and phenomenal in basically studying the sun itself, and we will see how they basically see the sun. I mean, it's important to know that what features of the sun or what features of the heliosphere you can measure from the radio, but I'll come to that part. And then of course, there is a Gauri Bidunur radio telescope at IIA, which also is kind of doing a lot of solar physics research. And then there is an upcoming national large solar telescope which has been planned, or it's in the planning stage, which is coming up in Ladakh, which will be a much larger optical disk, and this would basically be looking at the sun in optical waveband. So in addition to the space-based observatories which are already there, there is also a support from ground-based observatories which are actually existing in current India, in India as well, and of course elsewhere as well. Like VLA and so on in the radio band, people have been looking into this, but I just want to focus on mainly the Indian this thing. So now let us look slightly in more details of what really we want to kind of ascertain, or what do you really want to know about these space weather drivers that exist between sun and earth. So one thing which I want to highlight over here, because these are some things which are fundamental to understand what is the source of radio emission and what we can actually get from radio emission. So these heliospheric elements are those features which actually exist between the sun and earth, and this has been well observed. So this, what you see on the top, is basically Ulysses was one of the first kind of observatory which went to the poles of the sun to see actually the poles of the sun, which is very fascinating. Now Solar Orbiter is going there, but Ulysses was one of the first to do this, and it kind of went, it looked into the surface, so you can see over here the sunspot number. This was only the time when it was active. So you can see the sunspot number, it basically goes much low. So that means it's basically fecal, the sun is quiet, and you can clearly see that most of the emission that is coming from the sun is close to the equator. Okay, it's close to the equator. This red and blue line are basically what you can say is the speed, general speed of the, this is basically the outward IMF and this inward IMF. So you can think of it like magnetic fields. So magnetic fields are kind of very smooth, and most of the emission is mainly coming close to the equator of the sun, or the equator of the sun. But when we go into the active phase, you can see that the interplanetary magnetic field has kind of jumbled up. It has become highly turbulent, and the emission is coming from almost all directions of the sun. Everywhere. The whole sun is kind of blasting out emission in all directions. And then the moment you go more closer to the weaker time, again the polar emission has gone off, and it only mainly comes from the equator. So typically this was the first indication that there are two classes of solar wind which comes out from the sun. In the weak part, you have mostly the slow solar wind coming from the equatorial region up to 400 kilometers per second and so on. But during the active phase, you have also wind coming from the polar region. So now you can think of it as like a sun as a dipole magnetic field. You have, at the poles, you have almost open field lines. So the material can flow unhindered in the open field lines, and you can have very fast winds going up to 700 kilometers per hour. So this was the first observational evidence that the solar wind have mainly two categories. the slow solar wind, which mainly comes mostly close to the equator, where there are closed magnetic field loops, and then over here they are mainly coming from the poles, which are called the fast solar wind. And what is interesting is that you can see all the solar wind is not like smooth. It has lot of features, lot of turbulence associated with them. So this is like really turbulence. It's almost like everything is moving with some fluctuations. Okay, and now we will see, we will also understand that this is very important. Having a turbulent solar wind is extremely important to see why we can see things in radio as well. So this is a very important, this kind of is like a envelope that covers everything between sun and earth. So it's every time the sun is emitting a turbulent solar wind, either slow or fast, and it kind of covers this region between sun and earth. And in addition to the solar wind, sometimes you have coronal mass ejections. Coronal mass ejections, this is a very nice image. This is basically the image from very recent, 6th of March 2025, by a new instrument called PUNCH, which is a polarimeter, white light polarimetry. So white light, so basically what happens is that most of the photons are getting scattered because of the electrons that are present. So this kind of scattering in physics is called Thomson scattering, because you essentially scatter the photons there, and any Thomson scattered light is polarized in nature. So by looking at the polarization, we can actually image how the white light would be as you go away from the sun. So this is the sun, this is the coronagraph, and this is basically looking outside of the coronagraph. And you can very nicely see that this coronal mass ejection has a beautiful structure associated with it. And I'll talk about this structure even in more details as we go on when you want to kind of identify this particular structure. But I just hope that this movie works. Yes, I want you to focus on this movie. So here you can see this is the edge of the sun, and this is the more corona. And you can basically see what is really happening is that you have a coronal mass ejection being injected. You will see now. You see a coronal mass ejection being injected, and you can actually track that coronal mass ejection as it moves along. Let me play this movie again. So you can see, oh, this is the coronal mass ejection. This has been passed through here. So this is the inner heliosphere. This is I think Venus, and this is Earth. You can see how the coronal mass ejection from the surface of the sun, some activity has happened and it has passed through, and it is coming and hitting the sun and Earth. So you can actually image this, but as you can see that there are gaps over here. In between, you cannot basically capture everything. So this is close to the surface of the sun, this is near Venus, and this is basically near Earth. But you cannot really see what is happening in between all these features, okay? And most importantly, this has been taken up with satellites, twin satellites called stereo. So the way stereo works is, you have Earth, stereo A is on this side, stereo B is on this side, and it kind of moves along with the Earth. So it's basically like making a 3D movie. You have like multiple viewpoints to look at this. So for example, if stereo A is here and CME is going here, you can actually map this stereo A. If it is the Earth is here, stereo is here, you can actually map by looking at a different viewpoint than Earth itself. Okay, so that's why stereo A and stereo B have managed to get some idea on what is happening, but it is mostly closer, around 30 solar radius from the surface of the sun, whereas Earth is about 215 solar radius. So there is a huge gap that exists, which we do not have any idea how the CME moves in this gap. And the reason why we don't have any idea is because as the CME expands, its density falls down. And if its density falls down, then you do not have any emission coming from it, as far as white light emission is concerned. Because you see, your photon has to scatter from the electrons, but if the electron density itself is down, the emission becomes very, very weak. So you cannot basically observe these emissions at all. Okay, so you basically have a black, nothing in between. It's like 30 hours sun you see something, then blank, boom, and then Earth you measure something. So you don't know what is happening in between, nothing. You have no idea what is happening in between. Because there's no way to observe it. Punch is trying to do that, but it's still, it's also an experimental stage, in the sense like you have 4 microsats and so on, but still there is a lot of scope for understanding what is happening for the CME between about 30-40 arson to 200 arson. So this is a completely blind spot for any observatory, unless you go there and see what is happening. Okay, so that's what Parker Solar Probe and Solar Orbiter does, but that is only 2 points, this full shell of such a big thing, right? So that's where radio plays a very, very important role. Another aspect that I wanted to touch upon is the impact, and this is where I really want to highlight here that once the solar wind or the CME comes and hits the magnetospheric environment, you have particles, because these are all energetic particles which are being kind of advected towards the earth, and these are charged particles. When these energetic particles get connected to the magnetic fields, these charged particles will move along the magnetic fields. Now, certain energetic particles can go and hit and get kind of converged on the poles of the earth. Okay, and these poles of the earth, when these electrons actually kind of deposited on the poles of the earth, you essentially get the famous auroral emission. That is what you must have seen. Most recently on 11th May 2025, 11th May 2024, there was a huge event which was being observed, and this is basically how the fact of aurora, how the auroral image would look like in such kind of geomagnetic event. And in fact, the aurora went so down in the latitude space that you could even see some glow on the same day in Ladakh, that is just north of India. So imagine everything that is happening on the poles, typically at plus minus 60 latitude, it has almost come almost to India. Okay, so this is basically the impact that these space weather can have, and this auroral emission, as we will see, this auroral emission is not only true for Earth, it's true for any magnetized planet. And in fact, the emission that will come from other exoplanets, SKA will play an extremely important role to kind of see these auroral emissions in radio bands from exoplanets. So now the question is, how the sun looks in our, how the sun looks in radio band. We have been talking about all about in optical band, whatever space satellites we have, what we understand, what are the different drivers. But since the focus is on SKA, you really want to understand what is the emission processes in sun which actually gives rise to radio wavelength. There are 4 major emission processes. One is called the plasma emission. I'll talk about this, explain to you what this plasma emission is about, physics of plasma emission. Second is, I think you would know gyrosynchrotron emission. I think you must have studied over the last 3 days about synchrotron radiation. So what is synchrotron radiation? Can anyone tell me? But only motion can give? ठीक है, मैग्नेटिक फील्ड्स भी है, मोशन भी है, तो देगा क्या? Why will it radiate? ठीक है, I will move it at relativistic speed, no problem. But why will it radiate? Huh? It will accelerate or decelerate. And any accelerated or decelerated charged particle emits. Right? So that's the idea. It's not just that motion is there. It's acceleration and deceleration is important. So for gyrosynchrotron is also related to synchrotron, but since you mentioned synchrotron is for relativistic and cyclotron is for non-relativistic, gyrosynchrotron is a term for mildly relativistic electrons. So something which is not fully relativistic and not non-relativistic also. So gyrosynchrotron does the same process when it gets accelerated and decelerated in magnetic fields, but for mildly relativistic electrons. So that's what you expect. Then you also have Bremsstrahlung emission. So Bremsstrahlung emission is essentially called free emission. or breaking radiation, and that is because if I have an ion and an electron moves closer to the ion, there is, let's say, some impact parameter, the ion force, there is a Coulombic force which will kind of retard the electron. So let's say electron is free here and it is moving, but let's say it comes closer to an ion, there will be a force from the ion on the electron which will slow it down. And since it's decelerated, it will emit radiation. And then but it will move away. It will never get captured by the photon. So it's called free. It was free to begin with. It ended up free only, but there was an intermediate phase where there is a breaking of this electron, and that's when it radiates, and that is called free radiation. And this mainly happens in coronal densities. Typically, if you go at lower frequencies, which is what SKA also will observe, you can actually look that this all happens at the coronal region, and therefore at lower frequencies the sun looks much bigger than its actual size, the photospheric size. The photosphere basically, when you want to define a photosphere, it is a fact when your photon kind of escapes from that region. So it is like optical depth becomes less than 1. But for radio frequencies, it is a much larger emission zone because of this Bremsstrahlung emission, and at lower frequencies you can actually see the sun appears larger in size because the emission comes from the periphery and so on. And finally, there is a more complex phenomena which is called electron cyclotron laser emission. So I hope you have heard about laser. So there is something called as population inversion. So you have some population inversion and some emission that is coming. Laser, so laser is for light, laser is for microwave, but this actually is not actually there's no population inversion here, so that's slightly complicated here. I will not, if there are any questions I'll ask them later, I will talk about it later, but in general this is mostly gives it in microwave and radio emission because of interaction of very high energetic non-thermal particles and normal electrons. Okay, so this is a very kind of localized emission, but it is basically happening near the sun and also in the auroral region. So let us basically look into the most prominent of this emission, which is the plasma emission. Now, if I talk about plasma, you can say, okay, plasma is basically the fourth state of matter, ionized gas, and so on. But there are certain properties of the plasma which are very, very important. It distinguishes it from a gas. The first is quasi-neutrality. That means if I take a box or a large room of plasma, there will be almost equal number of electrons and negative ions and positive ions existing on an average over a large scale. That is called quasi-neutrality, almost neutral. And secondly, they kind of have something called as a collective behavior. That means a particular region of the plasma will behave in a collective manner. Okay, so the particular portion of the plasma will behave in a collective manner. Now, what do I mean by plasma emission? So let us take, there is a very nice intuitive diagram here. So you can take a slab, okay. So this region of the slab, so this is a slab of a plasma. So this is a region of the slab where you basically have a neutral region, and then what you do is, let's say in this particular assumption we will ensure that the ions are almost stationary, and what you do is you perturb the electron. So you kick, let's give a kick to the electron, okay. So basically what you do is you kind of perturb this electron or give a kick to the electron. What will electron do? Because of the perturbation they will move away from the ions. Because they move away from the ions, they will generate an electric field, because there is a charge separation. And this electric field is basically acting as a restoring force to bring back the electron towards its original position. It does not come back to its original position, it overexceeds. And then there is an opposite direction electric field, so it comes back. So essentially, if I give a perturbation to an electron in a background static ionic plasma, the electron will essentially move in a simple harmonic motion. Okay? So that's basically an electric field generated because of the charge separation, which is acting as a restoring force. It kind of goes back and so on. So it's just like a mass attached to a spring. You kind of pull the mass, it performs a simple harmonic motion. And the frequency of that simple harmonic motion is what is called as the plasma fundamental frequency, or the frequency with which these electrons oscillate about the mean rest ion position is what we call the fundamental frequency of the plasma. And that is true for all plasma, all plasmas. So it is something which is inherent to that plasma. Okay? And if you basically quantify this, it's a very easy calculation, very easy. You can actually write down the equation and do this, and you can find out the frequency, which I want to highlight it here, depends on the charge, the mass of the electron, this constant epsilon naught, and most importantly the density of the electron, number density of the electrons in particles per meter cubed. So the fundamental frequency is 9 hertz square root of NE. Okay? So now why this is important? This is true for all plasma. This is happening anywhere between the sun and earth, everywhere. All plasmas that are existing will have this fundamental frequencies associated with it. That depends on square root of number density. Now if I give you an example, let us take ionosphere. If you look at the ionosphere, that is a shell of ions around our earth. The typical density is about 10 to the power 12 meter cube, particles per meter cube, 10 to the power 12. So what is the frequency I'm talking about? Can anyone compute? So that is about 9 megahertz. Okay, so now this is a very interesting number, about 10 megahertz, 9 to 10 megahertz. What it means is that any radio frequency which is below 9 megahertz will get absorbed by the plasma in the ionosphere. So ionosphere is basically acting like a sheet which basically absorbs everything below 9 megahertz. Similarly, anything coming from outside which is less than 9 megahertz is kind of absorbed by the ionosphere. It can never reach Earth. It's kind of like a shield. Okay, so any frequency cannot go from Earth above, and neither anything from Earth can come inside. Nothing can come inside. So that's kind of like a shield which is basically been created by the ionosphere, and that depends on the density of the plasma which is existing over here. So such kind of plasma emission is also seen between the sun and earth, where the density varies, and you can have different frequency which will be absorbed, and above certain frequency they will be transmitted, no problem. All frequencies below 9 megahertz will be kind of killed, will be absorbed. Nothing can pass through up and down. Okay, so that's a very important aspect of plasma emission, and this is and this is also the emission. So any plasma of particular density will emit this much frequency, and this is basically what you also kind of capture in radio band as such. So now, so now the question is, if this is the situation, how do we use radio bands to basically observe what is happening within sun and earth? So as I told you, there is a blind spot between about 30-40 our sun to about 1 AU. So how do you see what is happening in between this? So the technique that radio astronomers use, and this is where SKA will play an immense amount of role because of its sensitivity it provides, is for a technique called as interplanetary scintillation. Okay, so I am sure that you have heard about twinkling of stars, right? बच्चे थे will twinkle little star, right? So why the stars twinkle? एकदम one person. Exactly, because atmospheric particles are atmospheric waves. So some waves are there in the atmosphere which kind of provides this kind of turbulent screen. So the light photons which are coming are basically kind of refracted alternatively. A similar concept is actually used here when you want to study interplanetary scintillation. It's basically like twinkling of stars, but here you are talking about twinkling of a radio source which is far away. So here you can think of some cosmic radio source like a pulsar or something. I think Mayuresh talked about yesterday on pulsar emission. So you can think of a radio source, pulsar, which is coming, and you have plain radio fronts which you would expect because the source is very far. So you have plain radio fronts coming in. But if there's a sun, there's an earth, there's your receiver here, what is going to happen is that there will be a constant flow of solar wind which is turbulently moving between the sun and earth, and this wavefront has to pass through this constantly fluctuating solar wind. Okay, and so this wavefront will be distorted, and this distorted wavefront is what you will receive here. So if you can actually isolate this distortion or kind of quantify this distortion, you will have an idea of what is basically the information of the turbulence in the intervening medium. Okay, so that's the idea behind interplanetary scintillation. So that's why with this interplanetary scintillation, you can actually sense what is the amount of density of material which is exactly intervening in between this region. So here is an real observation of Sun-Earth system from such interplanetary scintillation. So here you can see how the plasma is basically being modeled, or it is actual observations. This is from interplanetary scintillation. You have constructed how the plasma is basically evolving between the sun and earth. So now you can see how we can actually, for this particular thing, we can see the evolution of this plasma between sun and earth. There is no blind spot at all, because we can clearly see how basically this whole thing is moving, and by looking at that source we can actually sample, or multiple sources we can sample how this whole thing is basically moving, and so on and so forth. So this is a classical this thing of how an interplanetary scintillation works, and the basic physics basically over here, and then I will stop. The basic physics actually deals with something called as Fresnel diffraction. So diffraction, everyone has heard about diffraction? Has anyone heard about Fraunhofer diffraction? What is the Fraunhofer diffraction? अरे वो तो experiment हो गया. What is Fraunhofer diffraction and what is Fresnel diffraction? Has anyone heard about Fresnel diffraction? Huh? Yes or no? So what is Fresnel diffraction? If you have heard, you should know. Huh? And Fraunhofer, what wavefronts you have? Fresnel, you're partly correct. It's the cylindrical wavefronts, Fresnel. So what is the difference between Fraunhofer and Fresnel diffraction? Anyone? No. You see, the Fraunhofer diffraction is when you are treating the source at an infinite distance and the screen at infinite distance, so large distance. Whereas here you have the nearby interaction which is basically happening. So here is another, the distances are not very far. So what is basically going to happen is that you have a radio source like a pulsar, or even you can actually, it is not required to look at kind of extragalactic or galactic sources. You can also look at a satellite which is basically transmitting a radio emission, and then this satellite radio emission can pass through such turbulent medium, and you can basically make an understanding of what is the turbulent features over here. So you can think of a radio source, and this radio source is basically the emission is going here, and this is where the solar wind is, and this point and this point, this is actually called the solar elongation angle, epsilon, and this point to this point is basically a z distance, which is from where the wavefronts are getting distorted, it is coming. Now, there are experts here, but the idea is that it's very simple, that you basically look at the amplitude, and there is something called as a Fresnel distance or a Fresnel scale, which is related to wavelength with which you observe and this distance z between the earth and point where this thing is there. And this Fresnel, what you can say, filter or Fresnel diffraction filter acts like a bandpass filter. So all the scales about this, basically this is a perpendicular wave vector, so that is 1 by RF, so inverse of that. So basically all those scales which are slightly above this or in this range are kind of only observed, or they kind of sensitive to this Fresnel diffraction. So interplanetary scintillation is very suited to kind of give you an indication of what is happening to the solar wind at scales of between 100 to 1000 kilometers, because most of the times we observe this with 327 megahertz, which is about 92 centimeters. So that is the wavelength with which you are measuring your interplanetary scintillations. And with this wavelength, the scales that you are sensitive lie in the range of 100 to 1000 kilometers. So these are, you can think of these are like packets of solar wind which are basically moving, turbulent packets, and you are sensitive to those packets only, and your distortion basically, you can actually get the emission by convolving it with this filter function, and you can basically get what is really happening. You can actually kind of quantify the perpendicular wave vector and the Fresnel scale and so on, and most importantly, how the turbulence is kind of situated here. So these are the things that you can actually get from the interplanetary scintillation. And finally, as I told you that even the coronal mass ejection, when it is kind of ejected from the surface of the sun, you have no idea what is happening in between. And as we know that these coronal mass ejections are highly magnetized in nature. So you can see such a nice cartoon diagram. So you have a coronal mass ejection, it has this complex magnetic field, and then surrounding it, it has a sheath region where it has more turbulent magnetic field. Now, what is it? We have no idea how these magnetic fields are evolving, and especially between 40 arcsun to about 200 arcsun. We don't know anything of what is happening. And that's where, again, radio comes into play, because essentially you use something called as Faraday rotation. Faraday rotation is a technique with when you have a linearly polarized light passing through magnetic fields, there will be some sort of a rotation which will be essentially given by this formula, which is nothing but an integral of any. So basically, I am a receiver here, that's where your line of sight is. So I am integrating along the line of sight, and E, that is the number density that lies along my line of sight, and the component of B projected on my line of sight. Okay, so that's what is there, and that's the beauty of it, because now if you imagine that I have a radio source which I am looking at, and there is a CME which is passing by, or some structure which is passing by, and if I can basically compute this Faraday rotation, and for some way I can actually also measure, let's say any, let's say if it's a pulsar, I can use a dispersion measure to compute any separately, then I have an estimate of any, or I can use any model of any, then I will be able to kind of constrain on the property of the magnetic fields of the CME through Faraday rotation. So this is something state of the art, which state of the art in the sense that is a very nice technique what people use to basically quantify the structure of the magnetic fields as you go along. So this way you can make an idea or an estimate of how the CME's magnetic field is evolving in a region where you have no idea or you have no observation of CMEs. So this is why radio wavelengths are of extreme importance, and having SKA, which is highly sensitive, will help us better constrain these properties and gives them much better viewpoint as far as interplanetary scintillation and Faraday rotations are concerned. I'll stop here. Thank you.
Questions?
Yes.
Yes, sir.
You said that information about say from 30 solar radii to 200 solar radii. So how do we have information that what's going on near the sun surface? Because Studio A and Studio B observe over what's going on over Earth's surface. Then how do we observe over sun surface?
No. See, over sun surface, you have remote sensing observation being done. So you basically have an idea, like for example, suit all the remote sensing payloads which are there on IIT Indore also, gives you an idea what is happening closer to the surface of the sun. So whenever a flare happens or a CME happens, you know closer to the surface of the sun. Now the idea is that you see, when you want to study space weather, what is important is that you want to understand what is the time of arrival of the CME at Earth. Right? That is what you want to do. Now, if you kind of track the CME, you can track the CME up to 30 solar radius, but then there's a blind spot and then tongue hits. So you don't know what is basically happening in between, and that's where radio wavelength comes into play. You have all the information closer to the sun because you can do remote sensing observation. Look at the sun, like SUIT does, what is happening in the chromosphere, or even I think the Solar Dynamics Observatory. It gives you an indication of what is happening in the corona as well. So you have all sorts of information pretty close to the sun, but not very in between phase, which is basically tracked by the radio wavelengths. That's the idea basically.
And in the solar cycle that you shown, there were two lines. One was red, one was blue. So why was there different lines there?
No, these are just polarity lines. So north and southwards polarity. So this is the magnetic field polarity. So outward and inward polarity. So basically what it indicates is that the magnetic fields are going outwards like this and the magnetic fields are going inwards. So it's a dipole field. So it's a closed field. There is no magnetic monopole. So it's like going like this and then coming inwards like this.
Okay. And what is the exact difference between CME, solar flare, solar wind, solar energetic particles? Because all are emitting from the sun only.
No, they are all emitting from the sun, but there are different ways in which they are there. So not all solar flares will give CMEs, okay, and not all CMEs will be associated with solar flares. That is also one thing. Okay, so solar flares are actually bright spots. So sudden release of magnetic energy, giving you very, very bright signatures in X-rays mostly. Coronal mass ejection is a material being thrown in the inner heliosphere because of energy input. Solar wind is basically constant flow of material. Coronal mass ejections, by the way, have speeds of the order of 1000 to 1200 kilometers per second. It's tremendous speed with which they move actually in the inner heliosphere. Solar energetic particles are interesting. Solar energetic particles are present almost everywhere. Flares kind of initiate them. They are called impulsive solar energetic particles. Or because you know that solar wind itself is plasma, so you have some particles there lying around, and then let's say that you have a CME propagating through the solar wind, there will be shocks at the solar wind surface which can accelerate the particles even more. So they are called gradual solar energetic particles because they are slowly getting accelerated. Whereas flares will accelerate it impulsively, so they are called impulsive solar energetic particles. And solar cycle is basically an overall variation in the magnetic fields of the sun itself and the activity cycle itself. So these are the different aspects. They have a very different impact on the magnetosphere and ionosphere system.
Thank you.
Yes.
So before we impose Faraday rotation, do we have another way to preserve the initial polarization because it might get changed on the way towards?
Yes. Basically, see, what happens is that the polarization, if there is nothing in between, it will be preserved. So you will get the same polarization. So polarization is nothing but the electric field vector. So if there is nothing in between, it will come like this. But now what is happening is that in this particular thing, Faraday rotation, you have an intervening medium which has some density. So let us say there is nothing in between, but there is only the CME of certain density Ne and some magnetic field structure. Now because this polarization electric field will be basically going under rotation, and then ultimately you get the obtained electric field which has been rotated by certain angle, and that's that delta chi. So that's the idea. So if you do not have anything between, it will only give you that polarization. Then you can exactly get the magnetic field structure over there. But it's usually not the case. Usually you have all magnetic field structures and everything. Many things can change polarization. I mean, dust also kind of impacts the polarization. So several things can modify polarization, but this is one way of kind of getting the polarization affected. And that is related to Ne, which is the number density that lies between the source of the polarizer and the magnetic field which is intervening between them, not at the source. What is magnetic field in between them?
Thank you.
In Fresnel diffraction part, the major difference between Fresnel and Fraunhofer is the distances which you talk about, the source and the screen. There are finite distances, while in Fraunhofer they are considered to be infinite. So how the idea is preserved in at the distances which we consider like Sunner distances. So how the Fresnel diffraction is held in such cases?
No, see, you see, the Fresnel diffraction, you have a finite. So basically this Z here is typically 1 astronomical unit. Okay. Okay, you can think 1 astronomical is very large, but the point is that when you are basically measuring the distortion of the wavefront, the distortion in the wavefront is still pertained over here. If the distortion would have gone, yes, then I would have assumed it to be an infinite thing. But it is not true. You still get to see distortion. Otherwise, you will never observe IPS scintillation in some sense. And this distortion is mainly happening because of interferences happening because of these layers. Okay, and that kind of distorts it, and then you are essentially getting a wavefront which is distorted and coming to you. So that's why you are more suited to use Fresnel diffraction. And if you look at the image, you will see a ring-like pattern. Okay, and you basically will see that this distortion is related to this particular scale here. So that's called the Fresnel scale.
And the distortion which happens is makes the plane waves let's say non-planar in such cases, because if we again by distortion, if it stays at plane wave, so we need some kind of lens to
so the fact that there is distortion is because you have turbulent signatures here. So it's going like you don't know how it will interfere and diffract at this particular point. So you don't know this part. So, but that's why if you quantify distortion and you know that this is coming from there, you can actually see or at least make some understanding of how the turbulence or how the scales are distributed. Okay, I have not gone into details of this, but these scales are something called as the inertial range of the solar wind turbulence. Okay, that's where your there's a normal energy transfer happens from a larger scales to a smaller scales, and this mostly follows something called as a Kolmogorov spectrum. Okay, so that is all slightly more complex stuff, but the point is it's purely a scale where energy from higher length scales goes into smaller scales. So this is where this region is like conduit or is kind of a pathway to kind of transfer energy from larger scales to smaller scales.
Yeah, okay, thank you.
I think we can take the discussions offline. The TV are talking.
Maybe this guy, there's one question there was asked.
So when you have talked about the fundamental frequency of the plasma, so what external impulses or what external impacts create those perturbations?
You can always have something or the other thing moving, right? I mean, in the plasma, everything is, even if you look at solar wind, something or the thing is moving. You just need a little perturbation to kind of, you have a plasma in steady state, but then you have some flow which is going and hitting it. It can kind of disturb the plasma, or even a CME passing by, it can disturb the plasma, and if it disturbs the plasma, it will start emitting.
And same thing with the electrons in the interstellar medium or intergalactic medium also.
Sure, any plasma will actually have its own fundamental frequency. Okay.
And sir, in scintillation, how do they identify the distortion?
Oh, so this is something from the Fresnel diffraction. You basically, it's a more complicated formula. You have to kind of convolve the turbulent spectrum with the diffraction filter, and you can get the, I think the power spectrum, I think they will be more expert in telling all these things, how they do it actually, and I think Rohit will give you more idea about this.
So basically, if there is no scintillation, your source in the sky plane will remain at the same place, right? But then, if there is scintillation, it means what? It means that you are actually distorting the plane wave. So the plane wave is coming, there is a parallel wave, like we were learning, like parallel wave means the star is there. I will distort it so that this plane wave becomes like this. So it will perceive that it is coming from somewhere else. So it will image the same object in two different times. The time scale has to be maintained. Then you will see that it is moving. That is the scintillation.
And not only that, sometimes you see anisotropic scintillation. So sometimes some part is more brighter on some side than the other side. So then you can talk about the anisotropy in the turbulence. So there are several aspects, information you can get about the solar wind and the CMEs as you from this interplanetary scintillation.
Okay, offline.
Thank you.
As a token of appreciation, I would like to invite our Aditya to give a token of appreciation to Bhargav. Cameraman.
anyone have the attendance sheet with you?